In this video, we're going to learn how to use the chain rule. So as I often do, we're going to start with an example that we already know how to compute. So suppose I want the derivative of 3x minus 1 all squared. So without using the chain rule, what we would have to do is expand this out. Okay, so f of x would be 3x minus 1 times 3x minus 1. And we'd have to FOIL everything out. So we would get 9x squared minus 3x plus 1. So 9x squared minus 6x plus 1. And then we can take the derivative as 18x minus 6. Okay, so that would be our derivative. Obviously, if this power is higher than 2, we probably don't want to do that, right? Expanding it out takes longer and longer as the power gets higher. So what we're going to do is we're actually, and I called this f unfortunately, but so f of x, we're going to want to try and write it as a composition of functions. Okay, so let's call it h of g of x. So g of x is going to be my inner function, okay? So this is my inner one. So I see that this 3x minus 1 is sort of inside some other bit. Okay, so my inner function, g of x, I'm thinking I want it to be 3x minus 1. Okay, then my outer function, h of x, is just going to be x squared. Okay, now if I rewrite f prime of x, so what we already know. Okay, so we know the derivative is this. I can actually factor out a 6, and then it's going to be 6 times 3x minus 1. That's convenient. Look, I already see my 3x minus 1. Okay, but I can actually, the 6 is actually 2 times 3x minus 1 times 3. Right, so I just broke the 6 into 2 times 3. And then we can inspect each of these parts. Okay, so the 3, this is actually g prime of x, right? The derivative of g of x is just 3. And this other part is a little bit harder to see, okay? But if we look at h of x, h prime of x is 2 times x, right? So if I think about this x as also subbing in 3x minus 1 for that x, this part is actually h prime evaluated at our inner function, g of x. Okay, so this is actually the idea behind the chain rule. So it's the outer derivative. Okay, so this here is the outer derivative evaluated at the inner derivative multiplied by the inner derivative. Okay, that's actually how we do the chain rule. So let's see the formal rule. So if y is a function of u, so say y is f of u, okay, and u is a function of x, so u is g of x, then y would be f of u, which is f of g of x, because g of x is actually u. Okay, then I don't know why I wrote and here. Oh no, so then this happens and this is how we compute the derivative. Okay, so there's two ways to write it. Okay, so the first way is using the sort of Leibniz notation. So dy by dx, so the derivative of y with respect to x, you can do as the derivative of y with respect to u, but you need to multiply by the derivative of u with respect to x. Okay, or written another way, the derivative with respect to x of f of g of x, okay, is the outer derivative evaluated at the inner part, I'm running out of room here, times the derivative of the inside. Should have just made it a bit smaller. Maybe I'm going to fix that so it looks nicer. Okay, so this part, okay, is the outer derivative evaluated at the inner function. And then we have to multiply by the inner derivative. Okay, same idea here. So this is the outer derivative. Okay, now notice it's with respect to u. Okay, but because we want our answer with respect to x, you're going to want to put u is g of x after. Okay, and then here, this is our inner derivative. So that's the derivative of g of x, essentially. So let's try another example that we know the answer to. So if I want the derivative of x cubed to the power 4, okay, so first of all, without using the chain rule, x cubed to the power 4, this is x to the 12. You multiply those exponents. So that means that the derivative of this thing is going to be 12x to the 11. Okay, that's we know that. That's the power rule. Okay, now I'm going to try to do this with the chain rule, and I'm going to do it in both ways. Okay, so the u is going to be the inner function. Okay, so okay, so y is sort of the outer part, so that's x cubed to the power 4. So here's where we use our composition. So this part is my inner part. Okay, so that's what I want my u to be. I don't want this here. So y equals this, and u is equal to the inner part. So that means that y is actually u to the power 4. Okay, so then using the Leibniz notation, okay, dy dx is going to be dy du times du dx. Okay, so the y here, I want to use the equation with u. Okay, so this is going to be the derivative of u to the 4. So 4u cubed. Okay, and then the du dx is my u equation, and I want to take the derivative with respect to x. So I'm going to be multiplying by 3x squared. Okay, now I want to replace what u is because I want this in terms of x. So this is 4 times x cubed times 3x squared. I guess I can keep going here. So the numbers go together and make a 12. And then this first part, x cubed, this is x to the 9, times x squared. Okay, so that's x to the 2. So 9 plus 2 is x to the 11. Okay, which is what we thought the derivative should be. Okay, now using the other method, my outer function, f of x, is x to the 4. Okay, my inner function, g of x, is x to the 3. So then the derivative of f of g of x, okay, is f prime evaluated at g of x times g prime of x. Okay, so let's take the regular old f derivative. So f's derivative is 4x cubed. Okay, the g derivative is 3x squared. So I want my f derivative, okay, evaluated at g of x. So everywhere I see an x in my derivative, I actually want to put in g of x. So this is going to be 4. So instead of x, I put in x cubed, because that's what g of x is, cubed times g of x, which is 3x squared. Okay, so the better you get at this, the less you even write all this notation. Okay, this is the outer derivative evaluated at the inside bit, and this is the inner derivative. Okay, and again, we put these together, it's going to be 12x to the 11, okay, just like we thought. A lot of people, I think, find using the u version is actually a bit easier at the beginning because you don't have x's everywhere. So this part here that I did can be confusing because my derivative for f is in terms of x, and then I'm plugging in a function of x. So that does seem weird. So it's sometimes a bit easier that they're different when they're different variables. So I have a u here, and then I want to replace it with something to do with x. But you can use whatever you like best, okay? But like I said, the better you get at this, the more practice you do, the less of the notation you're going to write. So let's try some examples. Okay, so, and I'm going to try to do them both ways at first. So I want to break this down. So I see that this is probably my inside function, 2x cubed plus 5. So let's let u equal 2x cubed plus 5, and that means that y is u to the power 9. Okay, so dy dx is going to be dy du times du dx. Okay, now something I should have mentioned maybe on the last page. So these go together. Okay, we treat that as one thing. It's the derivative of y with respect to u and the derivative of u with respect to x. The way that you know the chain rule you've done it right, though, is that you get this canceling happening, and then you see dy dx, which is exactly what you want. Okay, so we can't actually do that canceling, but if the canceling works out, then you know that you're using the chain rule properly. So dy du, so that's the derivative of y with respect to u. Okay, so that means that I want to take the derivative of this equation here with the u's. So this is going to be 9u to the 8. Okay, and then I want to multiply by du dx. So I want to take the derivative of this with respect to x. So that's going to be 6x squared plus 0. Okay, and now what I want to do is just sub in my u. So this is 9 times 2x cubed plus 5 all to the power 8 times 6x squared. Okay, now if I rewrite this, I can put the 9 and the 6 together to make 54. The x squared maybe is at the front. And then I have 2x cubed plus 5 to the power 8. Okay, that would be my derivative. Oops. Okay, so or I could do this with x's. Okay, so y is f of g of x. Okay, now I need my f function and my g function. So g is like the u, that's the inside. Okay, and the f is like the u to the y with the u. So this is going to be x to the 9. Okay, so then we know f prime of x is 9x to the 8, and g prime of x is 6x squared. So the derivative of f of g of x, okay, is f prime evaluated at g times g prime of x. So that means I want to take this equation here, but everywhere that I see x, I actually want to put in g of x. Okay, so this is going to be 9 times 2x cubed plus 5 to the power 8. And then I want to multiply by the derivative of the inside, which is 6x squared, g prime of x. Okay, so this is the outer derivative evaluated at the inside bit times the inner derivative. Okay, and notice that it's the same. Okay, so that's going to simplify to the same thing over here. Okay, let's try a couple more, or a few more maybe. So again, I see this. I'm just going to do one method for each now. So I see this as my inside function. Okay, but maybe I want to break this up. Okay, so y is actually, or y prime, sorry, is going to be the derivative of the square root, okay, plus the derivative of 7, okay, which I know is 0. So I don't actually need to worry about that 7. So now I just want to look at this square root. Okay, so I have this inner function. I'm going to do the u1 this time. Okay, so let's let y, in fact, I'm going to change so I'm not using y here. So let's let w equal the square root of 2x to the 5 minus 3. Okay, and u be 2x to the 5 minus 3. So that means that w is square root of u. Okay, so then dw dx is dw du times du dx. So when I want to take the derivative of w with respect to u, I want to use this equation here. Okay, so this is u to the 1/2. So this is going to be 1/2 u to the minus 1/2. Okay, now I want to take the derivative of u with respect to x, so I want to use this equation here. So that's going to be 10x to the 4. Okay, so putting these together, this can go to the bottom, so it's going to be 10x to the 4 over 2. Now it's square root of u. So this is 2x to the 5 minus 3. And I can actually simplify with the 2. So the 2 cancels and makes this a 5. Okay, so my final derivative, so dw dx is going to be 5x to the 4 over square root of 2x to the 5 minus 3, which means that y prime, our dy dx, is actually equal to dw dx because of the 7 went away. So this is going to be 5x to the 4 over 2x to the 5 minus 3. Okay, so that's my derivative. Okay, so now I'm going to try and do this one using the other notation. Okay, but first I'm going to rewrite this one. So this is 2 times x squared minus 4 to the minus 1. Right, so I could rewrite it with a negative exponent. So then when I want to take the derivative, the 2 I can actually just multiply after. Okay, so y prime is going to be 2 times the derivative with respect to x of x squared minus 4 to the minus 1. Okay, so that is the constant multiple rule. Okay, so we can just pull that 2 out. And now I want to look in here. Okay, so this, it looks like my inside function. Okay, so I'm going to let g of x be that x squared minus 4, okay, and then my f of x is going to be x to the minus 1. So f prime of x is negative x to the minus 2, and g prime of x is just 2x. So when I take this derivative, it's going to be 2 times, okay, f prime evaluated at g times g prime of x. So that's 2 times negative, so g of x is x squared minus 4. Okay, so that's to the minus 2, times g prime of x, which is 2x. Okay, so this is the outer derivative, and this one is the inner derivative. Okay, now I just want to simplify this. So the negative exponent can drop to the bottom. The 2's can go together, so I'm going to have negative 4x over x squared minus 4 all squared. Okay, so that would be my derivative. Now, what we just did was actually something called the generalized power rule, which I think I already sort of gave you in the previous section So when we first discussed the product rule, but it makes more sense now using the chain rule, okay? So here, if you have a function, okay, f of x, that's some other function to the power n, okay? So that means this g of x is my inside function, okay? But my outside function, which I called f, but okay, so my outer function, I'm going to call h of x, is going to be x to the n. Okay, so then I know h prime of x is n times x to the n minus 1. So f prime is going to be, I'm going to write it down here, but it's going to be h prime of x, h prime evaluated at g of x, times g prime of x. So what that looks like is it's going to be n, okay, now instead of x here, I'm going to put in g of x. Okay, so it's going to be n times g of x to the power n minus 1 multiplied by the derivative of the inside. Okay, so this is what we call the generalized power rule, because now I don't have to have just x to the n. I actually can have a function to the power n, and I know how to evaluate that. Okay, so this part here is the outer derivative, and that part there is the inner derivative. Okay, so we get this generalized power rule. Okay, let's try a couple more examples. So, suppose a sum of $500 is deposited into an account with interest rate R% that's compounded monthly. At the end of 10 years, the balance is going to be given using this equation. So B is your balance. So your principal, the amount you've deposited, times 1 plus your rate over 1,200 to the power 120. Okay, you don't need to know where that formula comes from, but that's how you can find your balance. Okay, so what we want to know is at what rate is the balance changing when we have R as 5%. Okay, so if we're talking about a rate of change, remember that this is a derivative. So it's not over an interval, it's when R equals 5. Okay, so it's at R equals 5, so it's at a specific point. So we're talking about an instantaneous rate of change. So we want a derivative. So what we want to do is we want to determine b prime of R, so the derivative with respect to R, and then evaluate at R equals 5. Okay, but to compute the derivative, b prime, or b prime of R, we have a composition of functions. So I'm going to rewrite this function. So it's 500, 1 plus 1 over 1,200 times R to the power 120. So the 500, when we take the derivative, can just stay out front. Okay, that's the constant multiple rule. Okay, so it's going to be 500 times the derivative with respect to R of the remaining bit. Okay, now this looks like it's a function of R to a power. So we could use the generalized power rule or the chain rule. So it's going to be 500 times, so we take the outer derivative, so the outer bit is something to the power 120. So we bring the 120 down, and then we have the something, okay, so exactly as it was, to the power 1 less, so to the power 119. And then we need to multiply by the derivative of the something, the thing that we didn't touch. So you can think about the chain rule as actually like peeling an onion. So each time you take the derivative, you get closer to the middle. So you do the outer derivative, you leave the inside bit alone, okay? You remove the outside skin, and then you take the next layer off, so you take the derivative of the next layer, and then you can take the derivative of the next layer, and you can just keep going, and you multiply all these derivatives. Okay, Okay, so this is going to be 500 times 120, 1 plus r over 1200 to the power 119. And now I want to times by the derivative of this inside bit. So derivative of 1 is 0, and the derivative of a constant times r is just the constant. Okay, so I should have written this is, so this part is the outer derivative, and now we're doing the inner derivative. Okay, so now when you simplify everything, so this part over here, this is just a number. Okay, the 0 doesn't need to be there. So I can take this number times this number times this number. Okay, when I do that, I just get the number 50. Okay, and then I'm going to have 1 plus r over 1200 to the power 119. Okay, so now I can plug in b prime, I can plug in r equals 5. So that's going to be 50 times 1 plus 5 over 1200 to the power 119. And if you compute that, you get 82.01. Okay, so this is a rate of change. So the balance is given in dollars. Okay, so it's going to be dollars per, and then the units for r are percentage points. So it's going to be per percentage point. Okay, so that's at the rate at which my balance is changing. Okay, as the rate is changing. Okay, let's try another example. So here I actually have multiple layers going on. So I'm going to use a multiple chain rule. So I'm going to try and do this just with the layers idea. So my outermost layer, okay, is something to the power 5. Okay, so when I do y prime, okay, I want the outermost derivative. So it's going to be 5 something. Okay, so I have not touched this to the power 4. That's the outermost derivative. Now what I need to do is times by the derivative of the thing I just left alone. Okay, so this is the outermost derivative. Okay, but I left the inside bit alone. Okay, so the inside bit stays the same, and you just take the derivative of the outside bit. So imagine you have a box to the power 5. If you were going to take the derivative of that, it's going to be 5 box to the power 4. Okay, that's what we did. But now I want to multiply by the derivative of the box. Okay, so now to do that, I see that I have another composition. So now this thing is the inside. So my outer function is the sine bit. Okay, so the derivative of sine is cosine. So the derivative of sine of a box is going to be cosine of the box. Okay, and then I need to multiply by the derivative of the box. Okay, so this is the next outer derivative. Okay, now again, I have a composition of functions where my inner bit is the exponent of this exponential function. So I'm going to write all of these derivatives we've already done. Okay, now again I want to multiply by the derivative of e to a box. Okay, the derivative of e to a box is actually e to the box. Okay, so this derivative is its own derivative, but then I need to multiply by the derivative of what was in the box. So it's like the onion. Okay, we took off one layer, and then we have we want to take off the next layer of the onion. We want to take the derivative again. We still had something with layers. So now we want to take the layer off, the next layer off. And we just keep going until we run out of layers. So finally, I have something that's doesn't need to be a composition of functions. I know how to take this derivative. Okay, so it's going to be 2x. So I'm going to have 5 times sine to the power 4 of e to the x squared minus 1 times cos e to the x squared minus 1 times e to the x squared minus 1 times 2x. There's not a lot of simplifying that can happen here. If you want to put the 2 and the 5 together, you can, and move the x to the front maybe. Okay, so 10x e to the x squared minus 1, and then we're going to have sine power 4 e x squared minus 1 times cosine of e to the x squared minus 1. Okay, this would be our simplified derivative. Okay, so this one we had to use the chain rule 3 times. Okay, so here's the first time. We took the derivative of the outside multiplied by the derivative of the inside. And then to do that derivative, we had to take the derivative of the outside and multiply by the derivative of the inside. To do this derivative, we had to take the derivative of the outside and multiply by the derivative of the inside. So each time, that was the chain rule, using the chain rule. So in this step, this here is the next outer derivative. So you just keep going. Okay, there's one more thing I want to talk about. Because I did not justify the quotient rule at all, what I want to do is actually use the chain rule with the product rule to prove it for you. So if f of x is u of x over v of x, I can actually rewrite this as u of x times v of x to the power minus 1. Okay, so now I can think about this as a product. Okay, but this second one needs the chain rule to take the derivative. So then f prime of x is going to be the derivative of the first one, so u prime of x, times the second one as it was. So that's v of x to the power negative 1. And then I want to add the derivative of the second one. So I need to take the outer derivative is minus 1 v of x to the minus 2, and then multiply by the derivative of the inside. So that's v prime of x. And then multiply that by the first function. Okay, so that's using the product rule. It's just that the derivative of this needs the chain rule. So the derivative needs the chain rule here. Okay, now I'm just going to simplify this. So v of x to the minus 1, this part is actually u prime of x over v of x. Okay, now plus minus, that's going to be a minus. Okay, and then over here I have v prime of x, u of x, and then this negative 2 exponent is going to drop the v of x down to the positive 2. Okay, now I just want to make a common denominator, so I want to multiply by v of x and v of x. So multiply by our fancy 1. So I'm going to have u prime of x times v of x minus v prime of x times u of x all over the bottom squared. This is the statement of the quotient rule. Okay, so you can avoid the quotient rule and use the product rule instead if you're willing to use the chain rule. So a lot of people actually prefer generally to do this way. I don't know why, I just use the quotient rule, but if you want to use this way, the more comfortable you get with the chain rule, some people do like to use this method instead of the quotient rule. It works out the same way, okay? You get the same answer, doesn't matter which way you do. But, so as a justification, now hopefully you better believe anyway that the quotient rule is exactly what I told you it should be.